Hello, today we will be looking at problem 1.34, which asks us to test Stokes' theorem for the function v equals xy in the x-hat direction plus 2yz in the y-hat direction plus 3zx in the z-hat direction using the triangular shaded area of figure 1.34, which is shown in the top right corner here. And I have Stokes' theorem written out here for a refresher. To start off, we'll be focusing on the left-handed side of this theorem. So first we're going to want to just take the curl of v, which is this part of the equation right here, and then after that we'll take the dot product with dA. To start, we'll have the partial with respect to x, partial with respect to y, and partial with respect to z. And our components and 3zx. And to take the cross product, first we will have in the x-hat direction, so that will be partial with respect to y of 3zx minus the partial with respect to z of 2yz. And this is in the x-hat direction. And then we'll subtract from the y-hat direction, and that is going to be the partial with respect to x of 3zx minus the partial with respect to z of xy, and that is in the y-hat direction. And finally, we will add the z-hat component, which will be partial with respect to x of 2yz minus the partial with respect to y of xy in the z-hat direction. And we can simplify that. We will get the partial derivative of 3zx with respect to y is 0. So then we'll just have minus the partial with respect to z of 2yz. That will just be 2y in the x-hat minus the partial derivative with respect to x of 3zx is just going to be 3z, and the partial with respect to z of xy is going to be 0, so you don't have to subtract anything out there, so that's in the y-hat direction. And then in the z-hat direction, we'll have the partial with respect to x of 2yz is going to be 0, minus the partial with respect to y of xy is just going to be x in the z-hat direction. And I'm just going to simplify this as 2y x hat minus 3z y hat plus x z hat right here. Okay. Now that we have that, we want to, well, we can rewrite it over here. Now that we have that, we are going to want to find dA. And so as we can see over here, x is not going to be differing at all over this surface right here. X is going to be a constant at 0. So our only changing aspects are going to be y and z. So it'll be dy dz. And the direction is going to be in the positive x-hat direction, because of the way we are taking the line integral will be going around counterclockwise. So this will be our area element. Will be coming out of the page towards us in the positive x-hat direction. Okay, so therefore we can write dA as dy dz in the x hat direction. And we have x is constant at 0. And now the dot product of the curl of v and dA is just going to be, we're only going to worry about our x component because dA only has an x component, and so it'll be negative 2y in the x hat direction dotted with dy dz x hat, which is just going to give us negative 2y dy dz. Now that we have that, we need to find our limits for this integration. So we are going to, we can let z go, we can let y go from 0 to 2. So y will be going like that, but then that means that we need to find z as a function of y. So to do that, we can look at our figure here, and we can see if we considered z to be a function of y, z of 0 when y is 0 is going to be equal to 2, and we can find our slope using these 2 points. So that will be negative, it'll be y2 minus y1 over x2 minus x1, so where y2 is 0 minus 2 over 2 minus 0, so we will be getting negative 1 as our slope. So therefore, z will be going from 0 to 2 minus y, as negative 1 is our slope. And that is going to be the boundary for z, as z goes from 0 all the way up to this line, which we defined as z equals 2 minus y. Okay. Now that we have that, we can write out our integral. So we are going to let y go from 0 to 2, and z go from 0 to 2 minus y. It's important that we have z come first here, because otherwise our integral wouldn't make sense. We want to keep y in the integral for when we differentiate with respect to y. So now we can write out the whole integral, and we can see from here, we're just going to bring this down. It will be what we found up here, which is going to be negative 2y dy dz. And this isn't too hard. This will just become integral from 0 to 2, y from 0 to 2, and then z is just, it's going to be negative 2y z from 0 to 2 minus y, and we'll be now doing dy. Also, I had a mistake here. It should be dz dy. And then that's going to go from to this, which will be negative 2y, and then we'll have 2 minus y, excuse me, we'll plug in for z, and we're not going to plug, the 0 would take it to 0, so we can leave it as that, and dy, and then now we just have to integrate 0 to 2 of negative 2y positive 2y squared minus 4y, and that's dy. And now that is going to be equal to 2y cubed over 3 minus 4y squared over 2, so that'll be 2y squared. And that is going to go from 0 to 2, which is going to give us 2 times 8 over 3 minus 2 times 4. So we'll have 16 over 3 minus 8. And we can rewrite that as 16 over 3 minus 24 over 3, which gives us negative 8 over 3 as our final answer when we are using the left-hand side of Stokes' theorem. And now we can move on to the right-hand side of Stokes' theorem, where we will be taking the line integral around the bounded shaded region, the closed line integral. So that will be this part of the equation. And we can break that up into 3 different paths. So our first path will be 1 over here in red, second 2, third 3. But first, so actually I'm going to write that out. And we'll want to add up all of those path integrals, those line integrals, to get our final answer. So since we're in Cartesian coordinates, we can just say that our dl is going to be dx x hat plus dy y hat plus dz z hat. And therefore, when we dot dl with our vector, with our function, over here, we're just going to have x, y in the dx plus 2yz dy plus 3zx dz. I'm going to put parentheses to make it more clear. Excuse me. Okay. Now we're just going to go for each path one at a time. So our first path is going to take us, let's look at our diagram, it'll go from 0, 0, 0 to 0, 2, 0. So you can see just from this right here that our x and our z are not going to be changing. X and z are constants, and they're both going to be equal to 0, which means that dx and dz are going to be equal to 0. And our y is going to be going from 0 to 2. And so what that means is when we plug this into our integral, we'll be taking it from y equals 0 to 2. And our dx and our dz are 0, so we don't have to worry about those components up here. We can get rid of those. And then we just have to worry about the 2yz dy. However, we wrote up here that our z is equal to 0, so this also goes to 0, so this entire integral is equal to 0. Now for our path 2, that is going to take us from 0 to 0 all the way up to 0, 0, 2. And now here we can see that, again, x will remain constant at 0, but both our y and our z are going to change. However, since we are doing a line integral, we can't have two changing variables like this, so we need to make a function out of one of them in terms of the other, and we can just use what we found above, where we found that z goes from 0 to 2 minus y. We can just say here that our x equals 0, our z is going to be equal to 2 minus y. And then, in addition, our dx is going to, again, be equal to 0. And then our dz is just going to be equal to negative dy. which you could see very easily if you were to take the derivative of that. So then, moving on, and then we will have our y is going to go from 2 to 0. All right, so now for our integral, we'll have our y go from 2 to 0, but I'm actually just going to rewrite this as from 0 to 2 and just put a negative in the front, and that will just take care of that. And to be clear, it's y, and then we'll just have, now we only are worrying about our y changing, and so when we plug our dx and our dz into our equation above, we're going to get that we're integrating 2y, and we're going to plug in our z here, negative y plus 2 dy. And then our dz component, that doesn't immediately get canceled out. However, this z right here, this x right here does go to 0, so we don't have to worry about that term either. So this is going to be our integral, and that is just going to be equal to integral from 0 to 2 of negative 2y squared plus 4y dy, which is going to be our plus 2y cubed over 3 minus 2y squared, because it's 4y squared over 2. And then this is going to go from 0 to 2. And then that just simplifies into our 16 over 3 minus 8, which gives us negative 8 over 3 if we were to use the same fraction method as we used above. So there's our answer for path 2. And then now we can worry about path 3. So for path 3, we will be going from 0, 0, 2 back to the origin at 0, 0, 1. 0, 0, 0. And again, we will have that our x and our y are going to be constant and 0. And then our z is going to be taking us from 2 to 0. And again, our dx and our dy are going to be 0 because they are not changing. So then our integral becomes, we'll have z is going from 0, z is going from 2 to 0, but we can just make that be from 0 to 2 and put a negative here. And then we'll have 3z x dz. However, again, our x is going to be 0, so we don't need to worry about this. And we're just going to get a 0 for that integral. So then that means that our closed line integral of our v dot dl is going to be equal to each of these path integrals added up. So that'll give us 0 minus 8 over 3 plus 0, which just equals negative 8 over 3. And that is the same answer we got when we used the left-hand side of the equation. So this is it, and that is how you solve it. Thank you.